Okay, so we're going to go ahead and move on to this next section in Unit 9, which is not what my paper says here. This should be solve logarithmic, not exponential, excuse me, equations. Okay, so hopefully your paper has been changed and it does not say exponential right there, but if it does, go ahead and mark it out and just say logarithmic, because obviously we only have logarithmic equations on our paper. All right, so we are going to look at ways of solving logarithmic equations, and there's two types that we're going to come into contact with. We're going to look at equations where every single term has a log on it, okay? And we're going to look at ones like the ones on this page where there are terms that do not have logarithms, okay? So the ones where there are not logarithms are the little bit more challenging ones, I'll say. And then the ones where every term is a log term are the easier ones, so we're going to save them for the end, okay? So let's go ahead and dive in. It says solve the following equation for x, round to 4 decimal places, okay? So on our last one, remember it was rounding to 1 or maybe 2, so each problem may be a little bit different, so make sure you're paying attention to how your answers are to be rounded if necessary, okay? It may come out pretty. All right, so let's go ahead and look at these. It says log base 7 of 5x minus 3 equals 1, okay? So what I'm solving for is x, and right now it's stuck inside of this log. So I need to get what's inside the log out of the log, or I need to get rid of the log. So just like we did in our exponential section, right? We used logs to get rid of exponential bases. So here, to get rid of a log base, we can use the exponential base, okay? Remember that little one-to-one property that we talked about, how if we have the same exponential base on both sides, we can just drop the base, right, and be left with the equation? Well, we can go the opposite way too. We can start with an equation and we can stick in a little exponential base and bump that equation up into the exponent. So that's what we're going to do on these. The exponential base I want to use is the one that matches that of the log. So we're going to use exponential base 7. So I'm going to use 7 and move my equation up into the exponent. So 7 raised to the log base 7 of 5x minus 3 is equal to 7 raised to the first power, okay? If I put in an exponential base 7 on one side, I have to put in the exponential base 7 on the other side, okay? And my equation just moves up into the exponent. All right, so now we can use the inverse properties of logs to cancel our 7 and our log base 7. So we're left with 5x minus 3 equals 7. Then we go ahead and just solve this for x. So we add 3 to both sides, which gives us 5x is equal to 10. And then we divide off our 5. So we get x equals 2. Now, I'm not going to circle my answer yet because unlike exponentials, where it's okay to get anything in the exponent, we have negatives, 0, positives, logs are different. Logs, there are certain answers we cannot use because they're undefined for logarithms. So I'm going to go up here, just where we have some dead space here up at the top. Remember when we were dealing with logs? Well, here, let's even go back to exponentials. Okay, when we look at a to the x power, right, we're going to get a graph that either looks like this, right, or we're going to get a graph that looks like this. These are our exponentials, right? So all of our exponentials go through this point, right? 0, 1, 1, 0, that kind of thing. And then we swap all of our values, right? We swap all of our values, we end up with log base a of x. So we have two options for how those look, right? We either end up with something that looks like this, or we end up with something that looks like this. Okay, so those are our two options. Okay, we start with exponential, swap it, which gives us a log. So this is what any log problem looks like. So in these equations that we're solving for x. So if I look at these two log graphs and I am thinking about solving for x, notice there are certain x values that do not exist on this picture or on this picture, right? If I look at these two pictures and look, where do I not have defined x values? Notice I have no negative x's over here. My entire graph is over here on the positive side. Same thing here, right? I have no negative x's. It's all over here on the positive side, which means I also don't have 0, right? I don't have 0. That's where my asymptote is at x equals 0 on both of these. So anytime we're dealing with logs, okay, and notice our x goes inside the log, we can only evaluate it at positive values of x, okay? So I'm going to say can only have positive numbers inside a log. Okay, you can only have positive numbers inside a log. Now, this is talking about what's inside that log to be evaluated. It's not talking about your specific answer. Okay, so look at our answer. We got 2. Now, it doesn't matter if 2 is positive, negative, or 0. What I'm talking about is what's inside this log. We have to check that answer. So I'm going to write here, we're just going to check this inside quantity, because that inside quantity, whatever that equals, that's what we're plugging into our log base 7. So I have to check to make sure that 5x minus 3 ends up positive. I can't have negatives, and I can't have 0 inside this log. So if I look at 2, and I plug 2 back in here, 2 times 5 is 10, minus 3 is 7. So that's a positive 7. That checks out, so I can go ahead and box in my answer. Okay, so anytime you're dealing with solving log equations, you do have to check your answer to make sure whatever answer you get, when you plug it back inside these log quantities, that you're not getting a 0 or a negative inside this log, okay, or for that log quantity. So let's look at another one. Same idea here. I need to get rid of this common log that's out here so that I can solve for x. A common log's base is 10. So to get rid of log base 10, I'm going to use exponential base 10 and move that equation up into the exponent. Okay, if I put in an exponential base 10 on this side, I have to put in an exponential base 10 on this side. So now on the left-hand side, my 10 raised to my log base 10 cancels. So I get negative 6x plus 55 equals, anything raised to the 0 power, right, is 1. And then I can solve this for x. So I'm going to subtract my 55. So I end up with negative 6x is equal to negative 54. And then I divide off my negative 6, which gives me x equals 9. Okay, then again, okay, I don't even care what this number is, but I have to make sure when I plug that back inside my log that I get a positive value. So I'm going to go ahead and say we're going to check my inside value, which is negative 6x plus 55. I know a lot of you guys are going to be able to check these inside your head, but I'm going to encourage you to go ahead and write the word check and actually physically check it. Because if you're not checking it on your homework, you're going to forget to check it on the test, and you're going to forget to check it on the final. And I know in previous semesters, on our common final, there has been a problem where the answer that you get is one that doesn't work out. So this is an important step to remember when you're working logs. Okay. So if I take this 9 and plug it in here, negative 6 times 9 is negative 54. Negative 54 plus 55 comes out to a positive 1. So this does indeed check out. So I'm going to go ahead and just box in that answer. Okay. Let me look at another one that's a little different. Same idea, but it's a natural log. Natural log, we work the same way. We need to get rid of that natural log so that I could get inside of it to solve for x. And to get rid of a natural log, which is log base e, I'm going to use exponential base e. So I use exponential base e and raise my equation up into the exponent. If I put in an exponential base e on the left, I have to also put in an exponential base e on the right. So my e and my ln are inverses, so they cancel. And I'm left with negative 2x plus 96, okay, is equal to, now e squared, this is something we can do on our calculator. This is the e button on our calculator, and we just want to raise it to the second power. But I'm going to wait until the end to calculate it. So for right now, I'm just going to leave it as e squared, okay, so I can continue to solve for x. So I'm going to subtract 96 from both sides, which gives me negative 2x is equal to e squared minus 96. And then I need to divide off my negative 2. Okay. So that's going to give me x equals, and then again on your calculator, make sure you know where your E button is. Some of you will have an E button. Some of you will have an E to the X button. If you have this calculator, it's the second function here on your LN button, and mine says E to the X. So if I hit that second button, it says e to the, and then I have to put in what the power is. So I'm going to do e squared, close the parentheses so that I see that that's the only thing that is in the exponent of my e. And then I'm going to subtract 96, see what that equals, and then divide it by negative 2. Okay. So when I divide by negative 2, I end up with 44.305 471, blah, 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 blah. Okay. And on these, it said in the instructions up here, remember that we wanted to round to 4 decimal places. So I'm going to take this answer, go to my 4th decimal place, 1, 2, 3, 4, which is my 4. And then because there's a 7 behind it, that's going to round it up. So this is going to give me approximately 44.3055. Okay, and then again, before I circle my answer, I have to make sure that it's going to work out. So I'm going to check to make sure that the inside value of this log, which is negative 2x plus 96, stays positive. Okay, so if I take my answer, and again, you can use your, your calculator, 44.3055, and I multiply that by negative 2, okay, and then I add 96 to it. I just want to make sure that that comes out positive, and here it came out positive when I plugged it in, so that's a check, and I can go ahead and circle my solution. Okay, so I just want to go ahead and make a big note here. Note, you must always check your solutions when solving log equations. Okay, you must always check your solutions when you're solving log equations. So make a big fluffy cloud around that, or a big pokey bam sign, so when you're looking back over your notes, you don't forget to check your answers. Okay. All right, I want to look at a couple more similar to this, and then I'll have y'all try some. Notice here, this looks almost the same. Like if I didn't have this, that kind of looks like the problems we did before, right? And we can only get rid of this log by taking an exponential base 2 if we have just one log term here, right? That's our definition of logs. So the fact that we have 2 means I can't do that yet. So I want to try to write this as one log term, which means I need to condense it into one term. So to condense it, all I have to do is look at that operation. So my operation here is addition. We know that addition condenses into multiplication. So I can rewrite this as a 1 log base 2 logarithm by multiplying the inside values. So I have x minus 5 times x plus 10 equals 4. Okay. Now that I have just one log term here, now I can get rid of this log base 2. And I'm going to use exponential base 2 and put it in on both sides so that my equation moves up to the exponent. Okay, and I'm just going to write it in here. Big exponential base 2. Big exponential base 2. Okay, So my 2 and my log base 2 cancel. So I'm left with these two quantities, and I'm going to go ahead and multiply them out. Okay, so x times x gives me x squared. X times 10 is 10x. Negative 5 times x is negative 5x. And negative 5 times 10 is negative 50. Right? And it's going to be equal to 2 to the 4th power. And 2 to the 4th power is 16. Oh, excuse me. Okay, 16. All right, so I'm just going to look at what I have here. I now have an equation where I can solve for x because I don't have any logs or any exponentials really for that matter, but I have an x squared. And anytime I have an x squared, that's a dead giveaway that I'm either going to have to factor or use quadratic formula. So regardless of what my method choice is, I need this to all be on one side and equal to 0 so that I can either factor it or quadratic formula. Okay, so I'm going to subtract this 16, move it over, which will give me x squared. I combine my two x terms, so 10 minus 5 is a positive 5x, and then negative 50 minus 16 is negative 66, and that's equal to 0. So to solve this, I'm going to have to either factor or sum product, factor using sum product, or use the quadratic formula. And I don't care which method you use. If you really like the quadratic formula, have at it. I personally try to factor it always because that seems to be a little bit easier. So I'm going to look at sum product. My sum is my middle coefficient, which is a 5. And my product is my first coefficient, which is a 1, times my last coefficient, which is negative 66. So that gives me negative 66. So I'm looking for numbers that I can multiply to get negative 66 that I can combine to get 5. And I can actually use 11 and negative 6, right? Because 11 minus 6 gives me 5. 11 times negative 6 gives me negative 66. And the best part down here is my leading coefficient is a 1, so that means I can use the shortcut. Yay! So we know that these values that I got in my chart are going to be the values in my factored quantities. So I know that this is going to factor into x plus 11 times x minus 6. So now that I have it fully factored, I'm just going to solve each of these. So I get x equals negative 11, and I get x equals 6. So I got two solutions here, but they came from a log equation. So anytime there is a log equation, I know I have to check my answers. Okay? I have to check to make sure that all these quantities inside my logs stay positive. So I need to check that x minus 5 and that x plus 10 stay positive for both numbers. Okay, I like to write it out twice. If you just want to write it out once and check it for both, that's fine. So if I check negative 11 minus 5 is negative 16. So that one does not work, right? Now here's the thing. If it doesn't work for one, it is not a solution. So I don't even have to plug it into this one to already be able to say that x equals negative 11 is not going to work. Okay, so then we check 6. 6 minus 5 is 1. That's positive. 6 plus 10 is 16. That's positive. So x equals 6 is the only solution that I get here. Okay, now if it were not able to work, if it had given me something non-positive, and let's say negative 11 and negative 6 didn't work, then I would just write no solution. Okay, but if I have at least one that works, then I just circle it. Okay, I only write no solution if I have absolutely no solutions. Makes sense, right? All right, let me look at one more and then I will have y'all try one. Same thing here. I can't get rid of my log base 4 until it's condensed into one log term. I can see here that these two terms are subtracted, and subtraction condenses into division. So I'm going to go ahead and write this as just one log base 4 term, log base 4 term, by dividing these inside values. So I have negative 15x plus 20 over 5 inside my log base 4 is equal to 2. Okay, so now that I've condensed it into one log term, now I can use the exponential base to cancel out this log. So since this is log base 4, I want to put in an exponential base 4 on both sides. Okay, and I'm going to do that by just writing a big 4 here. Okay, so I put a big 4 in, so I've moved the equation up into the exponent. Now my 4 and my log base 4 will cancel. And I actually can cancel this 5 here, right? Because it divides evenly into these two. Or I can reduce both of them by 5. So that's going to leave me with negative 3x plus 4 is equal to 4 squared, which is 16. Okay. And then I just solve for x. So I subtract 4 from both sides, which gives me negative 3x equals 12. And then I divide off my negative 3. So I get x equals negative 4. And when I get x equals negative 4, I'm not going to circle it right away because remember, we have to check to make sure both of our inside log quantities stay positive. So I have to check negative 15x plus 20. I also need to check 5. Okay. So if I take negative 4 and plug it in here, negative 4 times 15 is positive 60. Plus 20 is 80, so that one works. And if I plug negative 4 in this one, well, I can't, right? Because there's no x. This is just a 5. It's a positive 5. It's going to stay a positive 5, so that works just fine. All right, so that means x equals negative 4 is a solution. So this is a good example of, we're not saying that you cannot get 0 or negative numbers as your answer. We're just saying that whatever your answer is, when you plug it in to check it, you cannot get a 0 or a negative inside that log quantity. Does that make sense? Okay, so there are 3 for y'all to try on this page and the next one. So take a minute and we're going to go ahead and pause the video, and whenever you are ready to check yourself, or if you need some help working through them, go ahead and unpause it and we'll go over them. Okay? All right, so let's look at these practice problems. The first one already has one log term already isolated for you. So all we have to do is put in that exponential base 2 to cancel out the log, which is going to leave us with our inside value 4x minus 16. On the other side, 2 cubed gives us 8. When we solve for x, we're going to get 6. Don't forget to plug it back in and check your inside value, which does come out positive. So our answer here is x equals 6. Okay. Notice your instructions here say to round to 4 decimal places. So if you get one that doesn't come out pretty, that's how you're going to round it. Okay. All right, let's look at number 2 and number 3. Number 2 needs to be condensed first, right? We have a subtraction. Subtraction condenses into division. So we're going to divide our inside values. Remember, the one that's subtracted is the one that ends up on the bottom. And then once we have it written as one log term, then we can go ahead and put in that exponential base to cancel out the log. So 5 raised to the log base 5 will cancel, and we'll be left with just this inside value, which happens to reduce, right? Because 3 goes into 24 8 times, 3 goes into 33 11 times. So we're left with 8x minus 11. And on the other side where we put in that exponential base 5, 5 to the first power is just 5. Okay, we go ahead through the process of solving for x, which we get 2, and 2 definitely checks out in both of our inside our log quantities, so it is our solution. Okay, all right, let's look at number 3. For number 3, we need to condense this one also. Addition condenses to multiplication, so we're going to write one log base 3 term with 8 plus x and x being multiplied inside. Okay. Once we have one log base 3 term, then we can go ahead and put in those exponential base 3's so that our 3 and our log base 3 will cancel. We'll be left with what's inside this log, which I went ahead and multiplied to get x squared plus 8x. On the other side where we put in our base 3, 3 squared is 9. And then because I have an x squared, that's a dead giveaway again, that I'm going to have to factor or do quadratic formula. So I need it equal to 0, not 9. So I moved my 9 over by subtracting, and then this is one that we can actually solve using the sum product chart. It should factor into x plus 9 and x minus 1. If you use the quadratic formula, it's totally fine. You should get the same answers. When we solve them, we get x equals -9 or +1. And when we check our inside values, -9 does not work. It gives us negative values, right? So the only solution we get here is 1. So down here at the bottom of the page, I've just kind of reiterated. We cannot do log evaluated at 0 because that's where our asymptote is. And we cannot do log evaluated at negative numbers. Okay, these are undefined. So that means that you cannot have a negative or a 0 inside the log when you check your solution. So be sure you always check your answers when you're dealing with log equations. Okay, so the good news is those were the hard ones. Yay, on to the easy ones. The easy ones are when you have logs on every single term in your problem. Logs on every single term make life easier because we have a one-to-one property of logs that says if we have log base A of m equal to log base A of n, then that is only true if m equals n. Okay? So what this is saying to me is if I have a log on both sides, right? No coefficients, same log base, then my inside the log numbers have to equal for this to be a true statement. So that means I could basically just drop those logs and get m equals n, okay? Or if I have an m equals n, just some equation that I know is true, I can stick in a log on both sides and come up with a log equation. Okay, so this is what we're hoping to do. We're hoping to get down to where we have 1 log equals 1 log so that we can just drop the logs. Kind of like we had the exponential bases. If we had the same exponential base on both sides, we can drop them. Same thing if we have the same logs on both sides, but it has to be 1 log term is equal to 1 log term. You can't have many, okay? All right, so let's look at how this works out. So on this first one, I have a common log is equal to a common log. There's no coefficients. It's a true statement. So I can just drop the logs. So this leaves me with 3x plus 12. I'm just going to go ahead and distribute that 3 in. Okay, is equal to, when I distribute what's inside this log, I get 6x. Okay. And now this is something I can easily solve. I subtract 3x from both sides. So I get 12 is equal to 3x. And then I divide off my 3. So I get x equals 4. So when I check my solution, I have to make sure every inside value stays positive. And I'm going to write everything that's inside the log. So when I check, I'm looking at 3 times x plus 4, and I'm looking at 2 times 3x. So if I plug 4 in here, 4 plus 4 gives me 8 times 3 is 24. That's positive. When I plug 4 in here, 4 times 3 is 12, times 2 is 24. That's also positive. So x equals 4 is my solution. Okay? Okay, let's go ahead and look at another one. Same thing here. I have ln of something equals ln of something. That's a true statement with no coefficients. So I can just drop the ln's. And I'm left with x minus 5 is equal to 2x plus 7, which I can easily solve, right? I just go ahead and move my x terms to the same side. I'm going to subtract 2x, which gives me negative 1x minus 5 equals 7. Move my 5 over to the other side by adding. So I get negative 1x is equal to 12. And then the last thing I do is divide off my negative 1. Okay, so I end up with x is equal to negative 12. And then remember, we have to check our inside values. So when we check, the two quantities that I'm looking at are x minus 5 and 2x plus 7. So when I plug negative 12 into x minus 5, negative 12 minus 5 is negative 17. That one does not work out. So if that one does not work out, then I cannot use this answer. And I didn't have any other answers. That was the only one that I had. So if my one answer doesn't work out, then my solution here is no solution. Okay, no solution. All right, let me look at a couple more. Same idea here, but notice on this one, I don't have one ln term equal to one ln term, right? I have two ln terms on the left-hand side. So before I can get rid of them, I have to condense them into one ln term. And since these are being added, we can condense addition into multiplication. So I'm going to write this as the ln of x times x plus 1 is equal to the ln of 20. And then now that I have one ln term is equal to one ln term, I can cancel the ln's. So I end up with x squared plus x, I just went ahead and distributed, okay, is equal to 20. And because I'm left with an x squared, I know I'm going to have to factor or use quadratic formula. So I'm going to go ahead and move that 20 to the other side. So x squared plus x minus 20 equals 0. And I'm going to try to go ahead and do some product. If that doesn't work, then I'll look at quadratic formula. So my sum here is a 1. My product is negative 20. And I can do this one, right? Because I find two numbers that multiply to give me negative 20 that combine to positive 1. And that is 5 and negative 4, right? And because my leading coefficient is a 1, I can use the shortcut, okay? So I know this is going to factor into x plus 5 times x minus 4 equals 0. And then I solve each of these. So I end up with x is equal to negative 5 and x is equal to positive 4. Once I have my answers, just like all the other ones we've done, we have to check our answers to make sure that we don't get anything negative or 0 inside those log quantities. So the log quantities that I have here are x, x plus 1, and 20. And I'm just going to write it under each one. X, x plus 1, and 20. Okay. When I check negative 5 and I plug it in for x, I get negative 5, which does not work. So the fact that just even that first one didn't work, I don't even have to plug them into the other ones. I know that x equals negative 5 is not one of my solutions. When I check 4, when 4 goes into x, it's just 4, which is positive. 4 plus 1 is 5, which is positive. And this 20 doesn't even have anything to plug into, it's just positive, right? So x equals 4 is my solution for that problem, okay? Let me look at one more, and then I will give y'all some to do, and that will be the end of this section. Yay! Okay, so this next one is another one where I can't just cancel all of my log base 7s. I mean, it's fabulous that they all have a log base 7, but I can only cancel it when I have one log base 7 is equal to another log base 7, and then I can drop them, okay? So I have to first condense this, right? It is being subtracted, and subtraction condenses into division. So I'm going to write this as log base 7 and the division of those two inside numbers. So x plus 11 on top, x minus 4 on bottom, and that's going to be equal to log base 7 of 4. Okay. So now that I have one log base 7 is equal to one log base 7, now I can drop my log base 7s. Okay. So I end up with x plus 11 over x minus 4 is equal to 4. And I want to stress the importance of making one log term on both sides before you drop it. Because notice, had you dropped all your log base 7s here, you would actually have these quantities being subtracted instead of being divided. Okay, so make sure you have one log is equal to one log before you get rid of the logs. Okay. All right, so on this one, I need to solve for x, but right now I have x's that are stuck in the denominator. I have that x minus 4. So what I'm going to do is I'm just going to go ahead and multiply on both sides by x minus 4. And the reason I'm doing that is so that on this left-hand side, I can basically cancel away that denominator. Okay. So when I do that on the left, all I'm going to be left with is x plus 11. And then on the right-hand side, I just distribute this 4 in, which will give me 4x minus 16. And now this is something that I can easily solve, right? I'm going to subtract x from both sides. So I get 11 is equal to 3x minus 16. And then I move my 16 to the other side. So I'm going to add 16. And I ran out of room, so let me come up here. So I end up with what? 3x equals 27. And then I divide off my 3, which gives me x is equal to 9. And then again, before I circle my answer, I want to make sure that I check that my inside quantities of all these logs stay positive. So I need to check x plus 11. I need to check x minus 4, and I don't really need to check 4 because it's just going to be 4, but it's a good habit to write them anyways, right? So we're going to start with x equals 9. 9 plus 11 is 20, which is positive. 9 minus 4 is 5, which is positive. And then our 4, which is not changing because there's no x in there, is also positive. So x equals 9 is our solution. Okay. All right, so there are 3 for y'all to try. So go ahead and work on those. Once you are done and ready to check yourself, you can go ahead and play the video again. If you happen to get stuck, go ahead and unpause it, and I'll help you work through it. Okay? Let's see how you do. All right, so on this first one, we have a regular log on both sides, so we can just drop it. And then we multiply over on the right-hand side because that inside value had multiplication inside the log, right? And when we solve for x, we should get -5. This -5 gives us no solution because when we plug it into either of these, right, we end up with a negative value. Okay, so no solution on number 1. On number 2, we have to condense first. Okay, so since we have a subtraction that condenses into division, here our division does not cancel out, right? But we can go ahead and drop our ln's now that we have one ln term is equal to one ln term. When we drop those, we can get rid of this denominator by multiplying by x plus 6 on both sides. So when it cancels out on the left, we're left with just x plus 10. And on the right, we just distribute that 3 in to get 3x plus 18. Continue to solve for x, and we get -4. Even though that's a negative number, when we check it inside all of our log quantities, they all come out positive. So our answer here is x equals -4. Okay? All right, let's look at our final one, which is number 3. Wait for it. Okay, number 3, we have to condense first. It's an addition, so it's going to condense into multiplication. So we get a multiplication inside here, but now we have log base 3 of something equals log base 3 of something, so we can drop our log base 3's. Okay, I went ahead and multiplied out what was inside our log, which gives us x squared plus x plus 5x plus 5, and from the right hand side we get 21. Because I have an x squared, I know we're going to have to factor it or do quadratic formula. So we need it equal to 0. So I went ahead and moved the 21 across. And when I combine all my like terms, I end up with x squared plus 6x minus 16. This is something that we can use the sum product chart to factor. So using the shortcut, because our leading coefficient is a 1, we end up with the quantities x plus 8 and x minus 2, which gives us the solutions x equals -8 and x equals +2. And then remember, we have to check our answers. So when we check our answers, -8 does not work out, +2 does work out. So x equals +2 is the only solution that we get here. Okay? All right, so that is the end of this section, which is solve logarithmic equations. So you should now be able to complete this assignment on your Alta Newton homework. If you have any questions, please let me know. I'm happy to help.